Hello there, and welcome to the Sleepy Science Channel. I'm so glad you've joined me tonight. Beneath quiet fields and sleepy villages on the French-Swiss border lies a hidden ring of astonishing size. It is buried deep underground, sealed away in silence. Yet inside it hums the largest scientific machine ever built, the Large Hadron Collider. Within this underground circle, particles smaller than atoms are sent racing at almost the speed of light. They collide in brilliant flashes that briefly mimic the birth of the universe itself. From those fleeting sparks, scientists have glimpsed the Higgs boson, recreated the primordial plasma of the Big Bang, and searched for answers to the mysteries of dark matter and antimatter. If you enjoy these gentle journeys, consider liking and subscribing. Or share your thoughts in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, there's nothing you need to do. Just let yourself settle, let your breath slow, and let the quiet vastness of physics open like a calm horizon. Now, if you're ready, let's begin. Some collisions reach temperatures hotter than the heart of the sun. Inside the Large Hadron Collider, when two protons meet head-on, the energy released is concentrated into a space smaller than the width of a human hair. For the briefest instant, the temperature soars to levels we cannot imagine, hotter even than the center of the sun. These collisions can reach trillions of degrees, recreating the kind of fiery state that existed only moments after the Big Bang. What's remarkable is that such extremes are not sustained. They flicker into existence and vanish almost immediately. Detectors surrounding the collision point pick up the faint signatures of particles born in these conditions, giving scientists a window into matter at its most fundamental level. In a sense, each spark inside the LHC is a miniature time machine, flashing us back to the universe's earliest and most chaotic moments. A major accident in 2008 once shut the collider down for over a year. Just 9 days after the Large Hadron Collider first powered up in September 2008, disaster struck. A tiny electrical fault in one of its superconducting magnets triggered a chain reaction. The magnet lost its superconductivity in an event physicists call a quench. Suddenly, thousands of amps of current had nowhere to go. The result was catastrophic. Helium coolant boiled explosively, magnets were torn from their mountings, and tons of equipment were destroyed. What had been planned as the dawn of a new physics era quickly became one of its biggest setbacks. Repairing the damage required more than a year of careful work and cost tens of millions of dollars. Yet the accident ultimately strengthened the collider. Engineers upgraded its safety systems, improved monitoring, and built in redundancies. By the time the LHC restarted in 2010, it was safer, sturdier, and better prepared to reach the incredible energies it had been designed for. The Higgs boson was finally discovered here after decades of searching. For nearly 50 years, physicists hunted for the Higgs boson, a particle predicted in theory, but never seen in reality. Without it, the standard model of particle physics was incomplete, unable to explain why particles have mass at all. The search stretched across generations, with experiments at earlier colliders coming close, but never succeeding. Finally, in July 2012, the announcement came. Both the ATLAS and CMS detectors at the Large Hadron Collider had independently observed a new particle consistent with the Higgs boson. It was a historic moment, filling an empty space in our understanding of nature. For Peter Higgs, the quiet theorist who first proposed its existence in the 1960s, the discovery was overwhelming. He sat in the audience in tears, surrounded by applause. The boson's confirmation reshaped physics, showing that fields permeate reality and give matter its weight, the invisible scaffolding of the universe itself. Collisions inside the LHC recreate conditions from the first moments after the Big Bang. When the universe was less than a millionth of a second old, it was a roiling sea of energy. Quarks and gluons drifted freely, not yet bound into the familiar protons and neutrons of atomic nuclei. The Large Hadron Collider is the only machine capable of recreating that primeval state. By smashing heavy ions together, such as lead nuclei, the collider releases so much concentrated energy that the quarks and gluons break free, forming a quark-gluon plasma. This strange matter lasts only for an instant, but during that moment, detectors capture its properties, how it flows, how it cools, and how it condenses into the particles we know. In studying these brief fireballs, physicists get to peek behind the curtain of creation itself. It's a way of rewinding the cosmic clock, replaying the very first chapters of the universe, not in theory, but in reality. The machine can melt atomic nuclei into a primordial quark-gluon plasma. Under ordinary conditions, protons and neutrons are locked together, their quarks tightly bound by the strong nuclear force. But when heavy ions are accelerated in the LHC and slammed together at near light speed, those bonds can be broken. The nuclei themselves melt into a quark-gluon plasma, a searing soup of matter more fundamental than anything found naturally today. It is not just hot, but extraordinarily dense, with particles jostling together in ways that defy classical physics. This plasma once filled the early universe before cooling into the familiar structures of matter. At the collider, scientists can create tiny droplets of this exotic stuff and watch how it evolves. The plasma's behavior offers clues to one of the deepest mysteries in physics: how quarks became bound into the protons and neutrons that make up stars, planets, and life itself. That plasma flows like a perfect liquid unlike anything found on Earth. What surprised physicists most about the quark-gluon plasma wasn't just that it could be recreated, but how it behaved. Instead of acting like a chaotic gas of particles, it flows like an almost perfect liquid, with astonishingly low viscosity. In fact, it is closer to a superfluid than to any kind of conventional matter. Imagine a liquid that resists virtually no flow, gliding effortlessly in every direction. That is what the detectors at the LHC revealed. This behavior challenges earlier assumptions about what the early universe was like. Rather than being a turbulent gas-like soup, the cosmos may have begun in a smoother, more liquid-like state. Studying this plasma helps researchers understand not only fundamental forces, but also the first steps of cosmic evolution, how order emerged from fire, and how the simplest particles condensed into bala, the building blocks of galaxies and stars. Discoveries at the LHC have already earned a Nobel Prize in physics. The discovery of the Higgs boson was more than a scientific milestone, it was a moment of triumph for human curiosity. In 2013, the Nobel Prize in Physics was awarded to François Englert and Peter Higgs, the two theorists who had first proposed the mechanism decades earlier. The prize acknowledged that their idea, once purely theoretical, had finally been confirmed in the flesh, or rather, in the fleeting traces recorded at CERN detectors. It was a rare moment when abstract mathematics was proven by experiment at the most fundamental scale. The Higgs boson discovery showed the world that the standard model of physics was right in one of its boldest predictions. And yet, by confirming it, the LHC also opened the door to deeper puzzles. Where the Higgs gave weight to matter, mysteries like dark matter and dark energy remain, challenges for the collider's future runs. The collider may one day reveal what dark matter is really made of. Dark matter is one of the universe's great enigmas. We know it's out there. Its gravity shapes galaxies, bends light, and sculpts the cosmos on the largest scales. Yet no telescope can see it, and no experiment has caught a particle of it directly. The Large Hadron Collider offers one of the best chances to change that. If dark matter has a particle form, high-energy collisions might produce it, leaving behind missing energy or unusual decay patterns in the detectors. Physicists scour the data for signs of these invisible particles, hoping for the first glimpse of the substance that outweighs all visible matter 5-1. The discovery would be nothing less than revolutionary, a key to unlocking a hidden half of the universe. For now, the search continues, with every new run of the collider offering another chance at a breakthrough. Physicists use the LHC to probe why matter outlived antimatter. At the birth of the universe, matter and antimatter should have been created in equal amounts. Yet if that were true, they should have annihilated one another completely, leaving behind only light. Instead, a tiny excess of matter survived, just enough to form all the stars, planets, and life that we know. Why? The answer remains one of physics' great mysteries. The LHC is uniquely equipped to investigate this imbalance. Experiments like LHCb specialize in studying subtle differences in the behavior of particles and their antiparticle twins. These asymmetries, called CP violation, might hold the key to explaining why the cosmos contains something rather than nothing. Each collision adds data to this puzzle, testing the standard model and hunting for cracks that could hint at new physics. In the end, the survival of matter, and of us, may rest on phenomena glimpsed only at the collider. Some theories suggest it could even glimpse extra dimensions. In popular imagination, extra dimensions belong to science fiction. Yet some serious physical theories suggest that hidden dimensions beyond our familiar three may exist, curled up invisibly at scales far too small for us to see. If true, their presence could affect the way particles interact. The Large Hadron Collider is one of the only tools powerful enough to look for such hints. Unusual patterns of energy loss, deviations from expected particle tracks, or the sudden appearance of new resonances could all point to physics unfolding in dimensions beyond our own. While no evidence has been found so far, the possibility remains tantalizing. If extra dimensions exist, they might help explain why gravity is so weak, or even offer clues to a unified theory of the forces of nature. In its collisions, the LHC gives us a chance to ask, is our universe bigger than it seems? Each beam stores as much energy as a speeding train. It can be difficult to imagine how much energy is stored in the circulating beams of the Large Hadron Collider. Each one carries the equivalent of a 400-ton train moving at full speed. That energy is packed into a stream of protons smaller than a strand of hair, racing invisibly around the ring. If released suddenly, the beam could melt steel, vaporize electronics, or carve through equipment in an instant. This is why beam management is so critical. The energy is both a tool and a danger. Engineers designed systems to guide the beam gently out of the collider when needed, dispersing it safely into massive blocks of graphite. In normal operation, however, the beams remain under exquisite control, circling continuously at near-light speed. It is a reminder that in particle physics, enormous power can be hidden inside something so small it cannot be seen with the naked eye. The beams race around the ring over 11,000 times per second. A single lap around the Large Hadron Collider is 17 miles long. Yet protons make that journey more than 11,000 times every second. This breathtaking speed is so close to the speed of light that even after billions of laps, the protons cannot go any faster. Instead, the energy poured into the system increases their momentum, making collisions more and more powerful. Each orbit is guided by an intricate system of magnets and monitored by sensors that ensure the beam remains stable. If you could somehow sit on one of these protons, the world would blur into nothing but the tunnel walls rushing by at unimaginable speed. But from a physicist's perspective, These countless revolutions are what makes discoveries possible. With every lap, the beams prepare for a collision, and each collision is another chance to glimpse the hidden architecture of the universe. The circular tunnel stretches for 17 miles underground. The Large Hadron Collider sits inside a tunnel that forms a perfect circle, curving beneath the Earth for 27 kilometers, about 17 miles. That's long enough to wrap around a small city, yet from the surface, it's almost invisible. The tunnel was originally excavated in the 1980s for an earlier accelerator, and later reinforced to house the LHC. Lying about 100 meters underground, it avoids disturbing towns and farmland above. Standing inside, you see a vast tube lined with superconducting magnets, pipes, and miles of cabling. Engineers must maintain this enormous ring with millimeter precision. Even tiny misalignments could disrupt the particle beams. The sheer scale of the tunnel reminds us that probing the smallest particles requires building on the largest human scales. It is an underground circle of discovery, built to let us peer into matter at dimensions a billion times smaller than the width of a human hair. The beams travel through pipes emptier than outer space. Protons inside the collider speed through vacuum pipes that are some of the emptiest places in the universe. To prevent stray gas molecules from interfering with the beams, engineers pump out almost every atom, creating a vacuum better than that of deep space. In fact, the pressure inside the pipes is 10 times lower than on the Moon. If even a few molecules were left behind, they could collide with the protons, scattering them and destroying the beam's stability. To maintain this pristine emptiness across 27 kilometers of tubing requires advanced pumping stations and constant monitoring. For the protons, the path is nearly frictionless, allowing them to circle for hours without significant energy loss. It is a reminder that sometimes what's most impressive is not what is there, but what has been carefully removed, an artificial void carved out to let matter race unimpeded. Thousands of superconducting magnets steer the particle streams. Keeping protons on track in a 17-mile ring requires a network of more than 1,000 magnets. These are not ordinary magnets like those on a refrigerator. They are superconducting giants, each stretching for meters and capable of producing magnetic fields more than 100, 000 times stronger than Earth's. Their job is to bend and focus the beams, guiding the protons into tight orbits and steering them toward collision points. The magnets work together like the muscles of an enormous machine, flexing invisibly to control particles racing at near light speed. If even one magnet drifts from alignment, the beams could be lost. Engineers spend years calibrating, installing, and monitoring this lattice of magnetism. The result is a kind of symphony of fields, invisible arcs shaping the smallest building blocks of matter, held together by the largest coordinated magnetic system ever created by human hands. Those magnets must be cooled colder than the vacuum of space. To generate their immense fields, the collider's magnets must operate in a superconducting state, where electrical resistance drops to zero. Achieving this requires temperatures close to absolute zero. The magnets are cooled to 1.9 Kelvin, colder than the empty void between stars, and even colder than the cosmic microwave background that fills the universe. At this temperature, the niobium-titanium wires inside lose all resistance, allowing currents of tens of thousands of amps to flow freely. The extreme cold also prevents the magnets from overheating, despite the massive energy they carry. It is strange to think of such frigid temperatures existing beneath warm fields and villages in Europe. But this hidden cold is the quiet foundation of the collider's power, a frozen ring that makes the hottest collisions in the universe possible. The collider uses the largest cryogenic system ever built. Maintaining more than 1,000 magnets at 1.9 Kelvin requires an enormous refrigeration system, the largest ever constructed. The collider's cryogenic network circulates liquid helium through miles of piping, keeping the entire ring colder than space. Cooling something so large is a massive challenge. It takes weeks to bring the system down to operating temperature, and once cold, it must remain stable for years at a time. The scale of the cryogenic system dwarfs anything used in industry, hospitals, or spacecraft. It is so effective that engineers sometimes describe the collider as the coldest place in the universe. Without this colossal refrigeration system, superconductivity would fail, magnets would quench, and beams would be lost. Instead, the cryogenics quietly hum in the background, making the extraordinary collisions at the heart of the LHC possible. It is an invisible ocean of cold, supporting the frontier of physics. Liquid helium flows through miles of pipes to maintain the cold. At the heart of the cryogenic system lies liquid helium, the only substance capable of cooling the magnets to 1.9 Kelvin. In total, more than 120 tons of helium circulate through a labyrinth of pipes stretching for miles around the ring. The helium is continuously compressed, expanded, and recondensed to maintain stability. Helium is rare on Earth. Once released, it escapes into space, which makes the LHC one of the largest single consumers of this precious element. Managing it safely requires incredible care, since sudden evaporation could release vast volumes of gas. But under normal conditions, the liquid helium flows silently through the system, a supercold lifeblood that allows the machine to function. Without it, superconductivity would vanish, the magnets would lose strength, and the collider would fall silent. This shimmering, invisible fluid makes the impossible achievable. If cooling fails, the magnets quench in a sudden burst of heat. Superconducting magnets are powerful but fragile. If even a small section warms above 1.9 Kelvin, resistance suddenly returns. The vast electrical current then encounters friction, releasing energy as a burst of heat. This event is called a quench. In a single instant, liquid helium can boil explosively, metal contracts and expands, and the magnet can be damaged or destroyed. Quenches are one of the greatest risks for the collider's operation, and engineers monitor constantly to prevent them. Safety systems are designed to detect the earliest signs of warming and dump the beam before disaster strikes. During the 2008 accident, a quench cascaded through many magnets, causing extensive damage. Today, improved monitoring keeps the collider safer. Still, the possibility is always there, a reminder that controlling the universe's smallest particles requires managing some of its most extreme engineering challenges. A single dust particle could disrupt the beam completely. Protons traveling inside the collider move in streams of extraordinary precision. But that precision can be fragile. If even a tiny speck of dust were to fall into the beam pipe, it could scatter particles, destabilize the stream, and destroy hours of preparation. Engineers take extraordinary measures to prevent this, assembling and sealing the vacuum chambers in ultra-clean environments. The pipes are baked at high temperatures to remove contaminants, and the vacuum pumps maintain pressures close to absolute emptiness. Yet the risk remains. In 2016, a wayward weasel chewed through a cable and triggered a shutdown. Even nature itself sometimes interferes with high technology. The lesson is clear. In the machine built to probe the deepest secrets of the cosmos, success depends on controlling not only energies beyond imagination, but also the tiniest details, right down to the echo. Possibility of a speck of dust. The detectors capture particle tracks with the precision of a giant digital camera. Surrounding the collision points of the Large Hadron Collider are vast detectors, each one designed to capture the fragments of particles that spray out after collisions. In some ways, they function like giant digital cameras, taking millions of snapshots every second. But their resolution is beyond anything in everyday technology. Instead of pixels of light, they record tracks of subatomic particles, their energy, charge, and direction. Each track is a clue, like a footprint left in sand, telling the story of what occurred in the instant of collision. These detectors allow scientists to reconstruct events that happen on timescales far shorter than a blink of an eye. Piece by piece, they build a picture of the invisible world inside matter, transforming the chaos of collisions into patterns that can be analyzed, tested, and compared with the predictions of physics. ATLAS is the largest detector, the size of a cathedral. ATLAS is one of the 4 major experiments at the LHC, and it is truly enormous. Buried underground, it stretches 25 meters tall and 46 meters long, weighing about 7,000 tons. Standing inside ATLAS feels like standing within a cathedral of science, its cavernous space filled with layers of detectors, electronics, and magnets. ATLAS was built to be a general-purpose detector, able to study a wide variety of particle collisions. It was here that much of the Higgs boson evidence was gathered. Its size is not just impressive, it's necessary. Particles born in the collider can fly off in any direction, and the only way to catch them all is to build a detector that surrounds the collision point completely. ATLAS is one of humanity's largest scientific instruments, a monument to our determination to capture nature's tiniest whispers on the grandest possible scale. CMS is equally powerful, but built in a totally different way. Just across the ring from ATLAS sits CMS, another general-purpose detector. On paper, it has the same goals: to catch the aftermath of collisions, search for new particles, and test the standard model. But its design is entirely different. While ATLAS emphasizes size, CMS emphasizes compactness and density. Its massive solenoid magnet, the Cs in CMS, produces one of the most powerful magnetic fields ever created for a detector, bending particle tracks tightly so that their properties can be measured with exquisite accuracy. CMS weighs more than 14,000 tons, yet it is packed into a smaller volume than ATLAS. Together, ATLAS and CMS provide a kind of double check. Each one can confirm the discoveries of the other. When both detectors independently saw signs of the Higgs boson, the world knew the discovery was real. They are twin sentinels, watching collisions from different perspectives. ALICE specializes in the physics of quark-gluon plasma. Unlike ATLAS and CMS, which aim to study a wide range of physics, the ALICE detector has a more focused purpose. Its name stands for a Large Hadron Collider experiment, and it is designed to investigate what happens when heavy ions collide at near light speed. These collisions produce quark-gluon plasma, a state of matter that existed just after the Big Bang. ALICE is optimized to measure the thousands of particles that stream out of such collisions, mapping how the plasma forms, flows, and cools. Its design emphasizes tracking and particle identification, making it uniquely suited to this work. By studying the plasma's properties, ALICE helps scientists understand how the universe transitioned from chaos to structure, from a formless soup of quarks to the stable protons and neutrons that form all matter. It is a window into the very first heartbeat of the cosmos. LHCb studies the subtle differences between matter and antimatter. The LHCb detector, short for Large Hadron Collider Beauty Experiment, has a special mission: to study why the universe contained matter rather than antimatter. According to theory, the Big Bang should have created equal amounts of both. Yet today, only matter remains. LHCb looks for subtle differences in the way certain particles, especially those containing A beauty or bottom quark, decay compared to their antimatter twins. These differences, known as CP violation, may hold the key to explaining why we live in the universe of something rather than nothing. LHCb is designed like a forward-facing camera, optimized to catch particles that shoot out in one direction from the collisions. Its results have already revealed surprising asymmetries, adding new pieces to the puzzle of cosmic survival. In a sense, LHCb asks one of the deepest questions of all. Why do we exist at all? Each detector contains millions of tiny sensors. Peering inside the LHC's detectors reveals layer upon layer of intricate sensors. These are not large instruments but tiny components, millions of them, working together like pixels on an enormous screen. Some detect light flashes as particles pass through. Others measure electrical signals when charged particles cross their fields. Still others track tiny ionizations or vibrations. The combined effect is a tapestry of measurements, capturing the details of collisions in 3 dimensions. Sensors must be extraordinarily fast, able to register events that happen in less than a billionth of a second. They also must withstand radiation levels that would destroy ordinary electronics. The detectors are, in many ways, living machines. Their hearts beating with millions of sensors, each one contributing a thread to the picture of the invisible. Without them, the fleeting events at the LHC would pass by, unnoticed and unrecorded. They record data at rates faster than any consumer technology. When collisions occur, the detectors produce torrents of information. Every second, they generate raw data at a rate far beyond anything in consumer electronics, more than 1 million DVDs worth per second. Of course, storing such volumes would be impossible. Instead, the detectors use complex trigger systems to decide in real time which events are worth keeping. These systems analyze incoming signals in microseconds, rejecting unimportant collisions and flagging rare, potentially interesting ones. Even after filtering, the saved data adds up to petabytes each year. To put it in perspective, the LHC's data output rivals or exceeds the largest tech companies. This flood of information is one of the collider's greatest challenges, requiring not only advanced detectors, but also vast computing resources worldwide. It's a reminder that modern physics is as much about data as it is about particles. The LHC produces 1 billion collisions every second. The scale of activity inside the collider is staggering. When both beams are running at full intensity, protons cross paths at 4 collision points around the ring. Each point can produce up to 1 billion collisions every second. Most of these are unremarkable, yielding well-understood particles. But hidden among the ordinary are rare events: a Higgs boson, a candidate dark matter particle, or a sign of new physics. To capture these gems, detectors and computers must sift through the noise with incredible efficiency. The sheer number of collisions ensures that even the rarest processes have a chance to appear. For physicists, it's like panning for gold in a rushing river. Most of what flows past is ordinary, but every so often, a glimmer appears that could change our understanding of the universe forever. Only a fraction are saved for analysis. Out of 1 billion collisions each second, only a tiny fraction, less than 1 in 1 million, are saved for analysis. The rest vanish unrecorded, discarded by the trigger systems that decide which events matter. This selectivity is essential, since storing everything would overwhelm the world's computing capacity. Deciding what to keep is a delicate balance. Physicists design algorithms to recognize signs of interesting events, such as unusual energy distributions, rare particle decays, or unexpected patterns. Sometimes discoveries are made precisely because something unusual slipped through. The process is humbling. The vast majority of the universe's secrets may still be flashing by unseen, lost in the data that must be thrown away. Air. Yet the collisions that are saved provide more than enough to fuel decades of analysis, keeping scientists busy and discoveries flowing long after each run ends. Supercomputers filter the signals in real time. The first line of defense in handling the LHC's overwhelming data is its supercomputing system. As collisions occur, electronic circuits and processors examine the signals within millionths of a second. They check for telltale signatures, a spray of particles, a sudden burst of energy, a rare decay pattern, and decide instantly whether to keep or discard the event. This process is called triggering, and it happens in layers. Simple triggers reject the obvious noise, while more advanced algorithms dig deeper into the patterns. By the time data reaches long-term storage, it has already been filtered down from billions of raw events to a manageable stream. These supercomputers are as much a part of the experiment as the detectors themselves. Without them, the LHC would drown in its own information. With them, the torrent of collisions is transformed into a steady flow of meaningful signals. The worldwide LHC computing grid connects universities across the planet. The data collected at the Large Hadron Collider is far too massive for any single computer center to handle. To solve this, CERN developed the worldwide LHC computing grid. It links together more than 170 computing centers across over 40 countries. Universities, laboratories, and institutions contribute their processing power, forming a vast distributed network. When data is recorded at CERN, it doesn't stay in Switzerland. Instead, it flows outward, traveling across high-speed internet connections to sites around the globe. Students in South America, researchers in Asia, and teams in North America all analyze pieces of the same puzzle. The grid makes the LHC a truly planetary experiment. It is not just a European project, but a shared endeavor that unites thousands of minds and machines worldwide. In a sense, the collider itself extends beyond its tunnel, existing as much in the digital cloud of humanity as in its underground ring. It processes more data than entire tech giants. The sheer data output of the Large Hadron Collider rivals, and in some cases surpasses, the biggest tech companies in the world. At peak, it produces tens of petabytes of data every year, equivalent to millions of HD movies. This torrent must be processed, filtered, and stored, with scientists combing through it for rare events. Google, Facebook, and Amazon manage vast oceans of user information, but the LHC's data is of an entirely different kind, fleeting traces of particles that exist for less than a trillionth of a second. Unlike social data, these signals cannot be recreated if missed. Every piece of information is unique and irreplaceable. This puts immense pressure on the computing systems to function flawlessly. The comparison makes clear, the collider is not just a machine of physics, but also one of the greatest challenges in information technology ever attempted. Artificial intelligence helps spot rare particle signatures. In the early days, scientists manually wrote algorithms to filter collision data. Today, artificial intelligence has joined the effort. Machine learning models are trained to recognize the faint fingerprints of interesting events hidden in the noise of billions of collisions. These algorithms can spot patterns too subtle for traditional methods: a slight asymmetry, a rare decay path, or a cluster of unusual tracks. AI doesn't replace human physicists, but it acts as a kind of scout, pointing researchers toward the collisions most likely to contain something new. In this way, cutting-edge computer science merges with cutting-edge physics. The same tools that power voice recognition or image classification are now being applied to the frontiers of the universe. helping sift through mountains of data to uncover the rare gems of discovery. Algorithms learn to discard trillions of unimportant events. For every meaningful collision recorded at the LHC, trillions must be thrown away. This is not carelessness, but necessity. Algorithms running in the detectors themselves act like gatekeepers, discarding events in real time. They learn what to ignore: common scattering patterns, familiar decays, unremarkable sprays of particles. The challenge is that hidden among the ordinary could be the extraordinary, so the filters must be finely tuned. Too strict, and discoveries vanish. Too loose, and the data flood becomes unmanageable. Striking this balance is one of the collider's great achievements. The fact that the Higgs boson was found at all shows that the system works. It is humbling to realize that most of reality's secrets flash past unseen, discarded in microseconds. Yet without this ruthless selectivity, the signals we do keep would drown in the noise. Physicists still manually interpret the most interesting collisions. Despite automation, despite artificial intelligence, the final step in understanding LHC data always returns to human judgment. After algorithms flag unusual events, teams of physicists analyze them carefully. They reconstruct particle tracks, measure energies, and test results against simulations. Human intuition plays a crucial role, noticing anomalies, questioning assumptions, and deciding whether a signal is real or just a fluke. Teams often work in parallel, checking and cross-checking each other's work to avoid bias. A single potential discovery may be debated for months or even years before reaching a conclusion. In this way, the collider combines machine efficiency with human insight. Computers catch the fleeting sparks, but humans weave them into meaning. It is a partnership that balances speed with wisdom, ensuring that each claim made from the collider is solid enough to reshape our understanding of the universe. Every claimed discovery must survive peer review worldwide. In science, no single experiment, no matter how powerful, can declare a discovery on its own. Every result from the LHC must pass through layers of review before being accepted. Within each collaboration, Atlas, CMS, ALICE, or LHCb, findings are scrutinized by hundreds of colleagues. Drafts are circulated, questions are raised, and analyses are repeated independently. Only when the internal review is satisfied can a paper be submitted to a journal. Even then, peer reviewers outside the collaboration test the claims. When Atlas and CMS both independently announced the Higgs boson in 2012, it was the weight of this process that gave the world confidence it was real. Peer review ensures that science is not about sudden revelations, but about careful, patient validation. It may slow the pace of announcements, but it guarantees that discoveries are not fleeting illusions, but lasting knowledge. The hunt for supersymmetry is still ongoing. Supersymmetry, often abbreviated SUSY, is a theoretical extension of the standard model of physics. It suggests that every known particle has a heavier, unseen partner. These partners could help explain mysteries like dark matter, unifying the forces of nature and filling gaps in theory. For decades, many physicists hoped the LHC would find supersymmetric particles. So far, none have appeared. This absence has forced theorists to refine, and in some cases rethink, their models. But the search is not over. With every run at higher energies and intensities, the collider probes new territory, looking for hints that supersymmetry exists. If found, it would revolutionize physics, opening doors to understanding the fabric of reality in ways we can hardly imagine. If not, the mystery only deepens, suggesting the universe may be stranger still than our boldest predictions. Supersymmetric particles could explain the mystery of dark matter. One of the most exciting possibilities of supersymmetry is that it could provide a candidate for dark matter. The universe is filled with unseen mass that outweighs visible matter by 5 to 1. We know it must exist because its gravity shapes galaxies and bends light, but no one knows what it is made of. Supersymmetry offers a possibility: stable, massive particles that rarely interact with ordinary matter, exactly the traits dark matter would need. If such particles are produced in LHC collisions, they would escape the detectors unseen, leaving only a trace of missing energy. This would be a telltale signature. Discovering dark matter at the collider would be one of the most profound breakthroughs in science, connecting the smallest scales of particle physics with the largest scales of cosmology, uniting the story of atoms with ETRs, the story of galaxies. So far, they have not been found. Despite years of searching, no supersymmetric particles have been confirmed. Each run of the collider tightens the constraints, ruling out possibilities one by one. To some, this is a disappointment. The elegant predictions of supersymmetry seem less likely with each passing year. To others, it is a source of excitement. Physics advances not only when theories are proven right, but also when they are proven wrong. The absence of Susie so far suggests that the universe may hold surprises beyond our expectations. It may force us to develop new theories, or even entirely new frameworks. Either way, the data from the collider guides the path. Even negative results are discoveries in their own way, narrowing the search, sharpening the questions, and reminding us that nature does not bend easily to human imagination. Each new run pushes the search to higher energies. The Large Hadron Collider does not stand still. After each shutdown for upgrades, it restarts with higher energies, brighter beams, and improved detectors. This relentless progress expands its reach into new territory. With every increase in energy, collisions probe smaller scales and rarer processes. If supersymmetry or other exotic particles exist, the collider may yet uncover them in the coming years. Even if they remain hidden, each run sharpens the standard model, testing its predictions with ever greater precision. The future high-luminosity LHC will multiply the number of collisions tenfold, increasing the chances of spotting rare events. Science at the collider is a marathon, not a sprint. Every upgrade is another step, every run another chapter. Together, they bring us closer to answers about the hidden matter of the universe and the deeper laws of reality. The Higgs boson exists only for a fraction of a second. The Higgs boson is one of the most fleeting particles ever observed. Once created in a collision, it vanishes almost immediately, decaying into other particles in less than a trillionth of a trillionth of a second. This means that scientists never see a Higgs boson directly. Instead, they detect the particles it decays into, photons, W bosons, or quarks, and reconstruct the invisible particle from its ghostly aftermath. Its short lifetime is why it took nearly 50 years to confirm its existence. Finding the Higgs required building a collider powerful enough to produce it and detectors sensitive enough to recognize its delicate traces. Its fleeting nature reminds us that reality at the smallest scales is full of phenomena too fast, too subtle, and too strange to grasp without extraordinary tools. The Higgs boson flickers into existence only to dissolve, leaving behind knowledge in its wake. Detecting it was like hearing a whisper in a storm of noise. The search for the Higgs boson was often compared to listening for a whisper during a thunderstorm. Each second inside the LHC, 1 billion collisions occur, filling the detectors with signals of known particles. The Higgs boson was hidden in this chaos, appearing only in a tiny fraction of events. Its signals were faint, subtle, and nearly drowned out by background noise. Physicists had to develop ingenious statistical techniques to identify patterns invisible to the naked eye. After months of analysis, what emerged was a slight excess of events, a small bump in a graph. That bump was the whisper of the Higgs. It was not dramatic or obvious, but quiet and persistent, growing stronger as more data accumulated. In this way, one of the greatest discoveries of modern physics arrived not with a flash, but with a whisper recognized among storms of data. Its discovery explained why fundamental particles have mass. Before the Higgs boson was confirmed, physicists had a puzzle. Why do some particles have mass while others, like photons, remain massless? The Higgs mechanism offered an answer. An invisible field fills all of space, and particles interact with it differently. Some interact strongly, gaining mass, while others glide through unaffected. The Higgs boson is the quantum signature of that field, the particle whose existence proves the field is real. By discovering it, scientists confirmed that mass is not an inherent property of particles, but something they acquire through interaction. This idea reshaped our understanding of matter itself. Without the Higgs field, electrons would not settle into atoms, protons would not form, and the universe would be an empty sea of light. The discovery was more than technical confirmation, it was an explanation for why anything, including us, has weight at all. Without it, atoms and stars could not exist. The importance of the Higgs boson is hard to overstate. Without the Higgs field, particles like quarks and electrons would remain massless, unable to bind together. Atoms would not form. Without atoms, there would be no molecules, no chemistry, and no stars burning in the night sky. The cosmos would be unrecognizable, a void of pure energy with no structure. In that sense, the Higgs field is one of the hidden foundations of reality. It operates silently, everywhere and always, giving matter its heft and allowing the universe to take shape. Discovering the Higgs boson confirmed that this invisible field exists. It was not just a triumph of theory, but a recognition that the very existence of stars, planets, and life depends on a delicate mechanism woven into the fabric of space-time itself. The Higgs is the quiet architect of everything we see. The Higgs field may have shaped the entire evolution of the cosmos. Beyond explaining the masses of particles, the Higgs field may have influenced the entire history of the universe. In the moments after the Big Bang, as the cosmos expanded and cooled, the Higgs field may have undergone a phase transition, a dramatic shift in its state. This transition could have determined how particles acquired mass, how forces separated, and how matter condensed. Some theories even suggest that fluctuations in the Higgs field could be tied to cosmic inflation, the rapid growth that set the stage for galaxies and stars. The LHC cannot answer all of these questions, but by studying the Higgs boson closely, physicists hope to learn how this field behaved in the universe's infancy. It is a reminder that something invisible, something silent, may have guided the grand story of creation from its very first chapters. The signal was found as a subtle bump in the data. When scientists finally announced the discovery of the Higgs boson in 2012, what they showed the world was not an image or a dramatic spike, but a modest bump on a graph. That bump represented an excess of events at a specific energy, consistent with the predicted mass of the Higgs. To the untrained eye, it looked like little more than a wiggle in a sea of statistics. But to physicists, it was a revelation. That small deviation carried the weight of decades of theory and billions of dollars of investment. It showed that beneath the noise, nature was speaking. It is humbling to realize that one of humanity's greatest scientific triumphs came not from something obvious, but from patient attention to a slight, persistent irregularity. Discovery, in this case, was a bump in the road that changed the map of physics forever. Billions of collisions were needed to confirm it. The Higgs boson does not appear often. Only about 1 in a billion collisions produces one. To find it, physicists had to sift through unimaginable numbers of events, collecting billions upon billions of collisions. Each one added a tiny piece of evidence. Over time, the data grew into a mountain, and the faint signature of the Higgs slowly emerged. This effort required the combined power of ATLAS and CMS, each detector independently checking the other's results. It took years of running, upgrades to the collider, and vast computing resources to confirm. In the end, it was persistence as much as brilliance that brought the discovery. The Higgs was not caught in a single moment, but revealed through patience, teamwork, and the steady accumulation of evidence until its presence could no longer be denied. The discovery was announced in 2012 to global celebration. On July 4th, 2012, scientists gathered at CERN and around the world to hear the results. The announcement was broadcast live, with thousands watching online and in lecture halls. When the graphs appeared showing clear evidence of a new particle consistent with the Higgs boson, the room erupted in applause. Decades of theory had been confirmed in a single morning. It was not just a moment for physicists, but for humanity. Proof that persistence and collaboration could uncover truths hidden at the smallest scales of reality. News outlets around the world carried the story, hailing it as the God particle discovery. For many, it was the first time particle physics captured global attention. The Higgs had stepped out of the equations and into existence, and the world celebrated together. Peter Higgs himself was in the audience, overcome with emotion. When the discovery was announced, one of the most moving moments came from Peter Higgs, the quiet British physicist who had first proposed the mechanism in the 1960s. Sitting in the audience, he wiped away tears as decades of work and waiting came to fruition. Higgs had spent much of his life unsure if his idea would ever be proven. Some colleagues had doubted it, and years of failed experiments had cast shadows of uncertainty. To live long enough to see it confirmed, and to witness the applause of his peers, was overwhelming. The sight of Higgs himself crying quietly among the crowd became an iconic image of the discovery. It was a reminder that science is not just equations and machines, but also human dreams, persistence, and the deep emotions of finally seeing an idea become reality. The Higgs discovery remains the LHC's greatest triumph so far. Though the Large Hadron Collider continues to search for new physics, the discovery of the Higgs boson remains its defining achievement. It solved a puzzle at the heart of the Standard Model and secured the machine's place in history. For many, the Higgs is a symbol of what humanity can achieve when thousands of people from around the world work together on a single goal. It proved that enormous machines, advanced technology, and patient collaboration could turn theoretical predictions into confirmed reality. While the collider has yet to find supersymmetry, dark matter, or extra dimensions, the Higgs stands as proof that the LHC delivers on its promises. It is the jewel of modern physics, fragile, fleeting, yet monumental, a particle that was once only a dream and is now one of the great discoveries of our time. The LHC shut down for upgrades after its first runs. After the excitement of its first discoveries, the Large Hadron Collider did not simply continue unchanged. In 2013, after the Higgs boson was confirmed, the collider was deliberately shut down for its first long period of upgrades. This pause, known as LS1 Long Shutdown 1, allowed engineers to strengthen magnets, improve power systems, and prepare the machine to reach even higher energies. The shutdown lasted 2 full years, during which thousands of people worked inside the tunnel, installing new components, and testing every part. Though it meant fewer collisions in the short term, the upgrades were vital for the long game. The LHC was never meant to remain static. It was designed to evolve, each shutdown preparing it for greater challenges. In many ways, the quiet years of maintenance are as important as the loud years of discovery, laying the foundation for future breakthroughs. Engineers doubled its collision energy. When the LHC restarted in 2015 after its first major shutdown, it did so with a dramatic leap in power. During its early runs, collisions had reached 8 tera-electron-volts TeV of energy. After the upgrades, that number nearly doubled to 13 TeV. To understand how impressive this is, imagine that each proton in the beam now carried the energy of a flying mosquito. Not much by everyday standards, but unimaginably concentrated in a particle smaller than a tau, billionth of a millimeter. By doubling the collision energy, physicists could probe smaller scales of reality and test theories that had been out of reach before. This increase transformed the collider into a sharper tool, able to cut deeper into the unknown. Each new level of energy opens doors to processes never seen before. And with 13 TeV, the collider became the most powerful scientific instrument ever operated. The upgraded machine is known as the High Luminosity LHC. The next great leap for the collider goes beyond energy. It is called a High Luminosity LHC, or ALHC, now under construction. Luminosity refers to the number of collisions that occur per second. By redesigning magnets, power supplies, and focusing systems, engineers aim to increase the collision rate by a factor of 10. This means far more data, far more rare events, and far sharper insights into elusive processes. Instead of making each collision more energetic, the HLHC will make them vastly more numerous, multiplying the chances of discovery. It is an evolution of the machine, keeping it at the forefront of particle physics well into the 2030s. When complete, the HLHC will not only extend the search for new physics, but also allow scientists to study the Higgs boson in far greater detail, turning a fleeting particle into a deeply understood cornerstone of the universe. It will deliver 10 times more collisions than before. At full design, a high-luminosity LHC will deliver around 10 times as many collisions as the current machine. This enormous increase will generate datasets so rich that even the rarest processes will emerge with clarity. Events that today occur only once in trillions of collisions may become observable on a regular basis. This upgrade is not about bigger explosions, but about statistics, the ability to see patterns that would otherwise be lost in the noise. For example, rare decays of the Higgs boson or subtle asymmetries between particles and antiparticles will become measurable. The trade-off is that the detectors will face an even harsher environment, flooded with signals that must be separated carefully. Yet this challenge is what makes the HLHC so exciting. With more collisions comes the possibility of moving beyond known physics and glimpsing entirely new phenomena. More collisions mean sharper insights into rare physics. In particle physics, rarity is everything. Some of the most interesting processes, such as the Higgs boson decaying into invisible particles, or matter behaving slightly differently from antimatter, happen only once in billions of events. To study them, physicists need not just energy, but vast numbers of collisions. That is why the High Luminosity LHC is so crucial. By producing an order of magnitude more data, it allows scientists to sharpen their measurements, reducing uncertainty and revealing fine details. A rare particle decay that once appeared as a faint blip in the data will, with enough collisions, stand out clearly. Precision is the goal, testing the standard model to its limits and searching for cracks where new physics might enter. More collisions mean clearer answers, and perhaps even new questions we haven't yet thought to ask. Thousands of components were rebuilt during the upgrades. Upgrading the LHC is not a matter of flipping a switch. It involves dismantling, repairing, and replacing thousands of components throughout the 27-kilometer tunnel. Magnets are removed and upgraded, cryogenic systems are reinforced, new cables are laid, and detectors are overhauled with improved sensors. Each component must be aligned and tested to extraordinary precision. During shutdowns, the tunnel becomes a hive of activity, with teams working day and night to prepare the machine for its next era. The scale of the work is enormous, yet it rarely makes headlines. Still, without these painstaking efforts, the Collider could not push forward. The upgrades are like rehearsals for a performance, invisible to the audience, but essential for the show to go on. Each new run is built on the sweat and care of thousands of engineers, technicians, and scientists. Even tiny misalignments could disrupt the beams. The protons in the LHC travel in beams narrower than a human hair. Keeping them on course through 27 kilometers of magnets requires near-perfect alignment. Even a deviation of a fraction of a millimeter can cause the beam to drift, scatter, or collapse. This is why alignment teams use lasers, sensors, and painstaking surveys to ensure every magnet is positioned with astonishing accuracy. The tunnel itself must remain stable, despite being buried in shifting Earth. Engineers regularly recheck alignments, adjusting components when needed. The precision is breathtaking. Guiding a proton beam is like aiming an arrow around the entire circumference of a city and hitting a target no larger than a pinhead. Such exactness may seem impossible, yet it is achieved every day at the Collider, a triumph of engineering matched to the delicate demands of fundamental physics. The tunnel must stay stable to within a few millimeters. Even the tunnel itself must remain extraordinarily stable. Though it is 27 kilometers long, its position cannot drift by more than a few millimeters, or the beams would no longer circulate properly. But Earth is never perfectly still. The ground expands and contracts with temperature, the crust shifts with tides, and tiny tremors ripple through the land. Engineers constantly monitor these movements, feeding corrections into the Collider's control systems. The tunnel's stability is also why it was built deep underground, insulated from much of the noise of the surface world. It is a reminder that the Collider is not just a scientific machine, but also a feat of civil engineering, a structure so precise that it must resist the subtle breathing of the planet itself. Within this stability, the fragile beams can trace their paths, round after round, toward discovery. Earth's tides and quakes can subtly shift the ring. Though it is anchored underground, the Collider is still part of a living planet. The gravity of the Moon and the Sun pulls on the Earth's crust, causing the ground to rise and fall by centimeters each day. Earthquakes, even ones far away, can send vibrations through the bedrock. These motions are small, but for a machine that requires micrometer precision, they matter. The ring flexes slightly with each tidal pull, and sensors pick up the gentle shifts. Corrections are made constantly, adjusting magnets and beams to stay aligned. In this way, the Collider dances subtly with the rhythms of the earth and sky. It is a striking thought. The tides that guide the oceans also tug at this underground circle of science, reminding us that even the most advanced machines remain connected to the movements of the natural world. The machine adjusts constantly to stay perfectly aligned. The LHC is not a static device, but a dynamic system, constantly adjusting itself to remain on track. Computerized controls monitor beam position, magnet currents, and environmental conditions in real time. When tiny shifts occur, whether from temperature, tides, or equipment, corrections are applied immediately. Feedback systems nudge the beams back into place, magnets are fine-tuned, and alignment is preserved. Without this constant vigilance, the beams would quickly drift and be lost. It is a kind of balance act, like spinning a plate on a stick, only carried out on a scale of kilometers and at speeds approaching light. The collider's ability to maintain this equilibrium is one of its most impressive feats, a quiet ballet of adjustments that allows it to push the boundaries of physics while remaining stable and safe. Each proton beam could melt hundreds of kilograms of metal. The beams circulating inside the Large Hadron Collider are not just delicate streams of particles, they are also immensely powerful. Each one carries the same energy as several hundred kilograms of TNT. If the beam were accidentally released onto a solid object, it could melt hundreds of kilograms of copper or steel in an instant. That kind of concentrated energy is both a tool for science and a danger that must be carefully managed. What makes it more astonishing is that all of this destructive potential is packed into a hair-thin stream of protons, invisible to the eye. The collider's design ensures that the beams never strike anything unintentionally, but their power is always respected. Controlling them requires one of the most sophisticated safety systems ever engineered. Proof that pushing science forward often means mastering forces that could easily spiral out of control. The beams are safely absorbed in giant graphite blocks. When it's time to end a run of collisions, the LHC cannot simply switch off the beams. Their enormous stored energy must be released safely. To do this, engineers guide the beams into massive graphite blocks designed to absorb the impact. Graphite is chosen because it can withstand extreme heat and distribute energy gradually. As the protons slam into the blocks, they scatter harmlessly, their destructive potential neutralized. These beam dumps are placed in heavily shielded caverns, ensuring no stray radiation escapes. The process may sound violent, but it is carefully choreographed, like bringing a speeding train to a smooth stop. Without the graphite absorbers, the beams could damage the collider itself. Instead, they end their journeys in a controlled way, leaving the machine ready for the next cycle of acceleration, collisions, and discovery. Engineers call this process a beam dump. The carefully managed end of the beam's life has a technical name: a beam dump. Though the term sounds casual, it describes one of the most critical safety operations in the collider. A beam dump can be scheduled at the end of an experiment, or it can happen suddenly if the system detects a fault. When triggered, special kicker magnets instantly deflect the beam out of its orbit, directing it toward the graphite absorbers. The switch happens in less than 1,000th of a second, preventing the beam from ever striking the wrong place. The process is a reminder that in high-energy physics, even endings are carefully designed. What could be catastrophic becomes routine, thanks to engineering foresight. Each beam dump is both an ending and a reset, clearing the way for the next sequence of acceleration and collisions. The shutdown sequence is carefully controlled to avoid disaster. Turning off the LHC is not like flicking a switch. Every shutdown follows a precise sequence designed to protect the machine and its components. First, the beams are safely dumped into absorbers. Next, the massive currents flowing through the superconducting magnets are reduced gradually, ensuring they don't quench. Then the cryogenic systems slowly adjust temperatures, avoiding sudden thermal stresses. The process takes hours, sometimes days, to complete. Any deviation could risk damage to the delicate systems inside. Engineers describe it as landing a plane, rather than turning off a car. Everything must happen in the right order, at the right pace. Only once the shutdown is complete can maintenance teams safely enter the tunnel. The careful choreography ensures that the collider, one of the most complex machines ever built, remains intact and ready for its next adventure into the smallest scales of reality. Safety systems monitor every magnet and sensor. With so much energy flowing through its beams and magnets, the LHC requires constant vigilance. Thousands of sensors measure current, temperature, alignment, and vacuum levels in real time. These signals feed into an intricate network of safety systems that watch for the smallest irregularities. If anything seems wrong, a slight rise in temperature, a sudden spike in current, the systems can intervene instantly. In some cases, they automatically dump the beam to protect the collider. This monitoring happens around the clock, whether the machine is running or resting. For the physicists and engineers who operate the collider, these safety systems are a reassurance. They allow the collider to push to extremes of energy and precision without constant fear of failure. It is a delicate balance between risk and discovery, made possible by thousands of eyes, electronic and human, watching the machine at all times. Any fault can trigger an emergency shutdown in microseconds. The collider does not wait for human intervention when things go wrong. If a magnet quenches, a sensor fails, or a beam drifts, the machine reacts faster than any operator ever could. In millionths of a second, protective systems can trigger a beam dump, ending the run to prevent catastrophe. These automatic safeguards are essential because of the enormous energies involved. By the time a human noticed a problem, it would already be too late. Instead, the collider is designed to protect itself, sacrificing beams rather than risking damage to magnets, detectors, or infrastructure. Operators may be disappointed when a run ends early, but the machine's survival comes first. This ability to act almost instantly is what allows the LHC to explore the frontiers of physics safely, despite harnessing energies powerful enough to vaporize matter. The 2008 accident was caused by a single electrical fault. The accident that struck the collider in 2008 did not begin with a dramatic failure, but with something as simple as a faulty electrical connection. In one of the thousands of superconducting magnets, a joint between two cables failed. The sudden resistance caused the magnet to heat, triggering a quench. Liquid helium boiled explosively, and the pressure damaged dozens of magnets. The chain reaction was devastating, spreading across hundreds of meters of tunnel. What made the event striking was how small its cause had been. A single weak link in a vast chain was enough to bring the world's most powerful machine to a halt. Since then, CERN has reinforced connections across the collider, ensuring that no single fault could trigger such damage again. The lesson was clear. In a machine of extremes, perfection in every detail is not optional, it is essential. Superconducting magnets failed and released massive energy. When the 2008 fault occurred, it unleashed a storm of energy. Superconducting magnets normally carry currents of thousands of amps with no resistance. But when they quenched, that current had to go somewhere. It was released as heat, tearing through metal and insulation. Helium, normally stable and quiet, boiled into gas and burst through the tunnel with explosive force. The magnets themselves, each weighing many tons, were shifted violently out of place. What had been a meticulously balanced system became a scene of chaos. It took days to assess the damage, weeks to plan repairs, and over a year to restore the collider. In the end, the accident taught hard lessons about the risks of managing so much stored energy. The LHC was rebuilt stronger and safer, proof that even setbacks can become stepping stones to progress. Entire sections of tunnel had to be rebuilt. The aftermath of the 2008 accident was sobering. More than 50 superconducting magnets were damaged, and parts of the tunnel were wrecked. Crews had to remove and replace massive components, some weighing tens of tons. Walls were repaired, wiring was replaced, and cryogenic systems were redesigned. The repair effort took more than a year, and involved teams from across CERN and partner institutions. While frustrating for scientists eager to resume experiments, the delay ultimately strengthened the collider. By the time the LHC restarted in 2010, it was not only repaired but improved, with reinforced joints and new safeguards to prevent similar failures. The rebuilt section stood as a testament to human resilience, proof that even in cutting-edge science, setbacks are part of the journey. The accident was a wound, but the recovery made the machine stronger than before. The repairs took more than a year and cost millions. Restoring the LHC after its accident was one of the largest repair efforts in the history of experimental physics. For more than 12 months, teams worked to remove damaged magnets, install replacements, and test every connection. The cost ran into tens of millions of dollars, a sobering reminder of how fragile even the most advanced machines can be. Yet the investment was necessary, and the payoff came quickly. By 2010, the collider was back in operation, and within 2 years it had confirmed the Higgs boson. The year of repair was not wasted, but a bridge between setback and triumph. It showed that science is rarely a straight path. Progress often runs through obstacles, delays, and disappointments before reaching discovery. The repaired collider became a symbol of persistence, turning failure into a foundation for success. Some feared the collider could create tiny black holes. When the Large Hadron Collider first prepared to switch on, a few voices worried about what might happen. One of the most dramatic fears was that it could create tiny black holes. The idea wasn't entirely random. Some speculative theories in physics did suggest that at very high energies, miniature black holes might form. To the public, the thought of a black hole opening under Switzerland was frightening. But physicists explained that if such objects were created, they would be microscopic and unstable. Far from being a threat, they would vanish almost instantly. Yet the image of a machine capable of making black holes caught the imagination, sparking stories far outside the scientific world. While the fear was unfounded, it revealed how strange and awe-inspiring the LHC appeared to those outside the field, a machine exploring realms most of us can barely picture. Physicists showed these would evaporate instantly. If tiny black holes could be formed in the collider, they would not grow or threaten Earth. According to the work of Stephen Hawking and others, small black holes evaporate through a process now called Hawking radiation. The smaller the hole, the faster it disappears, radiating away its energy. A black hole made at the LHC, if one could exist, would vanish in less than a trillionth of a second, leaving behind nothing but a faint signature in the detectors. In fact, physicists hoped such signatures might provide clues about extra dimensions or quantum gravity. Far from being dangerous, the idea was a potential doorway to discovery. The conclusion was clear. The collider was safe. Yet the notion of a machine probing energies where even black holes became possible showed just how far beyond ordinary experience the LHC was reaching. No real danger was ever expected. Despite the dramatic headlines that swirled before the collider's first run, scientists were never concerned about danger. They pointed out that the Earth is bombarded every day by cosmic rays, particles from space hitting the atmosphere at far higher energies than anything the LHC can produce. These natural collisions have happened for billions of years without harm. If high-energy crashes could threaten the planet, it would already have been destroyed long ago. The LHC is essentially recreating, in a controlled way, what the universe does naturally. By comparing cosmic rays to collider events, physicists reassured the public no catastrophic risks exist. Still, the fact that such reassurances were needed showed how unusual the machine seemed. Most scientific instruments do not inspire existential worries. But the collider's scale and ambition captured imaginations in ways that stretched far beyond physics. The machine has run safely for over a decade. Time has answered the early fears. Since 2009, the Large Hadron Collider has run safely year after year, completing trillions of collisions without incident. Instead of black holes, doomsdays, or portals, it has delivered scientific treasures: the Higgs boson, quark-gluon plasma, precision tests of the Standard Model, and new mysteries to explore. The machine is now part of the scientific landscape, its once feared power understood as a tool for discovery rather than destruction. For the people working at CERN, the collider is not a menace, but a marvel, the culmination of decades of design and construction, built not to end the world, but to better understand it. Its continued safe operation is proof that the fears were unfounded, and that imagination, when not guided by evidence, can easily stray into shadows that reality never confirms. Nevertheless, conspiracy theories spread around the world. Despite scientific reassurances, conspiracy theories blossomed as the collider prepared to start. Some claimed it would destroy the planet. Others linked it to supernatural forces, predicting that opening the collider would tear reality itself. Online forums filled with speculation, often far removed from the science itself. These stories were rarely believed by physicists, but they traveled widely, showing how mystery and fear can spread faster than facts. The collider became a character in a global drama, less a machine than a symbol of human daring and potential hubris. While scientists calmly explained the evidence, myths captured attention. In some ways, the theories were a backhanded compliment, proof that the LHC was so ambitious that people could scarcely believe it was real. The truth, though less sensational, was far more extraordinary. Not world-ending disasters, but glimpses into the deepest workings of matter and the cosmos. In 2012, some linked the collider to the end of the world. The year 2012 carried with it a cultural myth that the world would end, based on misreadings of the Mayan calendar. When that fear merged with the existence of the LHC, some people speculated that the collider would be the trigger. Blogs and videos claimed its experiments might tear space-time or unleash unstoppable forces. In truth, the collider was busy making careful measurements and collecting data that would soon confirm the Higgs boson. While fearmongers saw apocalypse, scientists saw discovery. When December 2012 passed uneventfully, the myth faded, but it remains a curious footnote in the collider's story. The fact that people linked the LHC to cosmic destiny shows how it had already transcended science in the public imagination, becoming a backdrop for larger cultural anxieties and fascinations about humanity's place in the universe. Others imagined it might open portals to other universes. Another popular myth suggested that the collider might open gateways to parallel worlds. While this was fiction, it grew from a kernel of real physics. Some speculative theories do propose that extra dimensions exist and that high-energy collisions might reveal them. But if extra dimensions could be glimpsed, they would not appear as doorways or tunnels. Instead, they would be subtle distortions in particle behavior, tiny shifts in energy distributions recorded by detectors. No portals, no gateways, just mathematical signatures in the data. Still, the story of portals captured imaginations, fitting into long traditions of myths about hidden worlds. In the end, the LHC has not found such evidence, but the search continues. The truth is quieter and harder to picture, but no less profound. A careful quest for signs of unseen dimensions woven into the very fabric of reality. Scientists patiently debunked these myths. Physicists did not respond to fears with mockery, but with patience. Again and again they explained the realities of cosmic rays, black hole evaporation, and the safety of the machine. Public outreach became part of CERN mission, not only to share discoveries but also to build trust. Lectures, interviews, and even open days at the Collider helped demystify the machine. In time, the conspiracies lost their grip, replaced by wonder at the real achievements of the Collider. The process showed how science must sometimes battle not only the unknown, but also misunderstanding. By addressing fears openly, CERN turned skepticism into curiosity. The myths faded, while the evidence remained. What was left was not fear, but appreciation for the grandeur of a machine that dared to probe the smallest structures of nature and the deepest questions about existence. The Collider's real wonders surpass any science fiction. As strange as the conspiracies were, the truth has been far stranger and more wonderful. The Higgs boson, long predicted but unseen, was revealed. Quark-gluon plasma, the stuff of the newborn universe, was recreated in a lab. Particle interactions were mapped with precision never before possible. No science fiction portal could rival the fact that the LHC allows humanity to glimpse conditions that last existed a trillionth of a second after the Big Bang. The real achievements of the Collider do not threaten the world, they expand it, giving us new eyes with which to see. Myths may capture attention, but facts hold wonder. The LHC shows that the actual universe, when studied with care and courage, is more astonishing than any imagined catastrophe or fantasy. Its true purpose is expanding human knowledge of the universe. At its heart, the LHC is not a weapon, a portal, or a danger. It is a question made of steel and magnets. What is the universe really made of? Every collision is an attempt to peel back one more layer of reality, to test theories and reveal truths. Its discoveries add to the chain of human knowledge that stretches back through Galileo, Newton, and Einstein. The Collider is humanity's attempt to understand itself and its place in the cosmos. The myths that swirled around it were distractions, but they also reflected the truth. The Collider touches on questions so profound that people instinctively connect them to destiny, to fear, to awe. Its true legacy, though, is quieter and deeper, an expansion of what we know and what we can imagine about the universe we call home. The LHC can accelerate not just protons, but heavy ions too. Most people picture the LHC smashing protons together, and that's true for much of its work. But the machine can also accelerate heavy ions, like lead nuclei. Instead of a single proton, these carry dozens of protons and neutrons bound together. When they collide, the results are even more dramatic than proton crashes. Whole atomic nuclei are broken apart, unleashing enormous energy. These special runs, called heavy-ion collisions, allow physicists to study matter under the most extreme conditions ever recreated in a laboratory. They give a unique glimpse of the forces that shaped the early universe, and they complement the precision work done with protons. This flexibility, being able to switch from light particles to heavy ones, is part of what makes the Collider such a versatile tool for discovery. These collisions recreate matter as it was microseconds after the Big Bang. When heavy ions smash together in the Collider, they melt into a searing fireball. In that instant, temperatures soar to trillions of degrees, and the familiar structure of matter breaks down. Protons and neutrons can no longer hold together. Instead, their building blocks, quarks and gluons, spill into a freely moving soup. This is the quark-gluon plasma, the form of matter that filled the universe just millionths of a second after the Big Bang. Studying it is like building a time machine, one that lets us peek into conditions that no longer exist naturally. The plasma cools and vanishes almost instantly, but for a fleeting moment, it reveals the raw ingredients of the cosmos as they were in its earliest heartbeat, before stars, before galaxies, before even atoms themselves had formed. The quark-gluon plasma behaves unlike any material on Earth. You might imagine that such a hot, dense soup of quarks and gluons would act like a chaotic gas, particles flying apart in every direction. Instead, physicists found something surprising. The plasma behaves more like a liquid, but not just any liquid. It flows with a smoothness that surpasses anything known on Earth, almost as if it were a single, unified substance. This behavior stunned researchers because it suggested that the fundamental building blocks of matter can move collectively, bound together in ways not expected at such high energies. The discovery showed that even at extremes of temperature and density, nature hides unexpected patterns and laws. The plasma isn't just exotic, it's teaching physicists that matter has properties far stranger than the solid, liquid, and gas states we encounter in daily life. It flows with almost no resistance, like a perfect fluid. Physicists often describe the quark-gluon plasma as the most perfect fluid ever observed. Unlike water, honey, or even liquid helium, it offers almost no resistance to flow. Imagine pouring a liquid that glides without turbulence, without friction, spreading instantly and smoothly. That's what the plasma seems to do, even at temperatures of trillions of degrees. This property makes it unique in physics because it sets a record for the lowest viscosity, the measure of a fluid's resistance to motion ever measured. In some sense, the plasma is more perfect than anything in the everyday world. Discovering this nearly perfect liquid was one of the LHC's great achievements in heavy ion physics. It tells us that at the smallest scales, when matter is stripped to its most basic form, it can behave with a grace and order that defies our ordinary expectations. Studying it reveals how protons and neutrons first formed. The plasma is important not just for its strangeness, but because it bridges a gap in cosmic history. In the early universe, quarks and gluons eventually cooled and locked together, forming the first protons and neutrons. These, in turn, became the building blocks of every atomic nucleus. By recreating the plasma in the collider, physicists can watch the conditions under which this transition occurred. They can test how quarks froze into the stable structures that have endured for over 13 billion years. In this way, the collider lets us study the very first chapter in the story of matter's stability. Without that moment of formation, no atoms, stars, or galaxies would ever have emerged. By understanding it in detail, we gain insight into why the universe is filled with complex structures and why it is not just an endless soup of energy. The plasma may hold clues to the nature of the strong force. Quarks are held together by one of nature's 4 fundamental forces, the strong nuclear force. It is the most powerful of them all, and yet it operates only at subatomic scales. In the plasma, where quarks and gluons are free, the strong force behaves differently than inside protons and neutrons. Measuring that difference is a way of probing the force itself under extreme conditions. Theories of particle physics predict how the strong force should act, but the plasma provides a real-world testbed. Each heavy-ion collision is like a miniature laboratory for examining the strongest glue in the universe. By doing so, scientists are not only solving puzzles about the early universe, but also about one of the fundamental interactions that make reality possible. The strong force binds quarks into protons and neutrons. To appreciate the strong force, imagine the tiny scale at which it works. Quarks, the smallest known constituents of matter, are bound so tightly by this force that they have never been observed alone. They are locked in groups of 3 to form protons and neutrons, or in pairs to form mesons. Without the strong force, quarks would fly apart instantly, and matter as we know it could not exist. The force is carried by gluons, particles whose very name reflects their role as the glue of the universe. In everyday life, we never notice this hidden power because its effects are confined within atomic nuclei. But in the collider, we glimpse it directly, watching it at work as quarks interact, bind, and transform in the energy of collisions. Without it, atomic nuclei could not exist. The strong force doesn't stop at holding quarks together. It also acts across short distances to bind protons and neutrons inside atomic nuclei. Normally, positively charged protons should repel one another, the same way two magnets push apart. But the strong force overwhelms this repulsion, gluing the nucleus together and making stable atoms possible. Without this invisible hand, no atom could last more than an instant. There would be no hydrogen, no carbon, no oxygen, no chemistry, no biology, no stars or planets. The very existence of complex matter rests on this force. By recreating extreme conditions in the collider, physicists can see how the strong force behaves under stress, deepening our understanding of the essential interaction that holds reality itself together. The LHC lets physicists test this force under extreme conditions. One of the unique strengths of the collider is its ability to push the strong force into regimes it has never been tested before. In the plasma, where quarks roam free, the force reveals new behaviors. Theoretical models predict how it should act, but only experiments can confirm or challenge those predictions. By colliding protons and heavy ions, the LHC maps out how the strong force scales across different energies, densities, and temperatures. This testing is not just academic, it is essential for building a complete picture of the standard model of physics and for pointing the way to what might lie beyond. The collider is like a laboratory where the strong force itself can be bent, stretched, and examined, showing us both its limits and its enduring power. These experiments push physics into entirely new territory. The study of quark-gluon plasma and the strong force is not merely an extension of older experiments, it is a leap into new ground. No previous machine has reached these energies, densities, or temperatures. The collider is charting territory never before explored, and each result adds a new page to the map of physics. Some of what is found agrees beautifully with theory, some raises new puzzles. That tension between expectation and surprise is what makes science thrive. The LHC is not only confirming our models of the universe, but also probing where they might break down. In the uncharted territory of quark-gluon plasma, there may lie hints of physics we have not yet imagined. These collisions are more than spectacular. They are the frontier of our attempt to understand the fundamental nature of everything. CERN operates the collider as Europe's premier physics lab. The Large Hadron Collider is housed at CERN, the European Laboratory for Particle Physics. CERN began in the aftermath of World War II as a vision for rebuilding European science through collaboration rather than competition. Over the decades, it has grown into the leading center for exploring the smallest building blocks of the universe. The LHC is its crowning achievement, the largest, most complex machine ever constructed. From its headquarters near Geneva, CERN manages not just the collider, but also the detectors, the computing grid, and the vast flow of scientific results. It is the hub where ideas, technology, and international teamwork converge. Without CERN careful stewardship, the collider would be impossible to operate. It is a living reminder that science flourishes most when it is shared across borders. CERN stands for the European Organization for Nuclear Research. CERN name is a reminder of its origins. In French, it was called Conseil européen pour la recherche nucléaire, the European Council for Nuclear Research. Though its mission has expanded far beyond nuclear physics, the original acronym remained. Today, CERN is synonymous with cutting-edge discoveries in particle physics, but its roots still echo in its name. This simple four-letter word is recognized worldwide, not just by scientists, but by anyone who has heard of the Higgs boson or the world's biggest collider. Behind it lies a story of nations pooling resources, knowledge, and imagination to do what no single country could achieve alone. The name may be rooted in history, but its meaning has evolved into a symbol of science at its grandest scale. It is one of the largest scientific collaborations in history. Running the collider is not the work of a single lab or even a single country. It is the combined effort of thousands of scientists, engineers, and technicians drawn from across the globe. The experiments connected to the LHC, ATLAS, CMS, ALICE, LHCb, and others are each collaborations in their own right, with research teams spread across continents. Together, they form one of the largest organized scientific communities in history. This scale allows not only the sharing of costs and technology, but also the blending of perspectives and expertise. No single mind can process the torrent of data or manage the precision of the machinery, but together, as a global network, humanity can. The collider is as much about cooperation as it is about physics. More than 10,000 scientists work on the LHC. The numbers are staggering. Over 10,000 scientists contribute to the LHC's experiments, making it the largest scientific workforce ever assembled for a single machine. These researchers specialize in fields ranging from quantum theory to cryogenics, from software to detector design. Some analyze collision data in offices far from Geneva. Others spend their days deep underground, maintaining the delicate detectors that record each proton smash. This vast community forms a tapestry of human effort, each person contributing a piece to the puzzle. It is a living demonstration of how science has become a global endeavor. The collider is not just a machine, it is a village of scientists united by curiosity and the desire to understand what the universe is made of. Researchers come from over 100 countries. The LHC is not only European. Scientists from more than 100 nations take part in its work, from the largest economies to small developing countries. This diversity gives the collider a truly global character. Walk through CERN cafeteria and you will hear a dozen languages at once, all threaded together by the shared vocabulary of physics. Collaboration on this scale is rare in any field, and it turns the collider into more than just an experiment. It is a cultural meeting place. Students, postdocs, and senior researchers alike find themselves working side by side, learning from one another while contributing to a shared mission. In a world often divided by politics, the collider stands as a reminder of what humanity can achieve when it unites around curiosity and discovery. The United States also plays a major role despite being outside Europe. Though CERN is a European organization, the United States contributes heavily to the LHC. American scientists help design, build, and run many of the collider's experiments. Funding from US institutions supports the detectors, the computing infrastructure, and the analysis of data. In return, American researchers are part of the discoveries, publishing results side by side with their European colleagues. This transatlantic partnership reflects the scale of the challenge. No single region can shoulder the cost or complexity of the collider alone. The participation of the United States and many other non-European nations makes the LHC a truly global project. It is science without borders, driven by the recognition that the mysteries of the universe belong to no nation, but to all of us. Planning the collider took decades of work. The LHC did not appear overnight. Its design and approval were the result of decades of proposals, debates, and international agreements. As early as the 1970s, scientists were dreaming of a machine powerful enough to probe the Higgs boson and beyond. Building it required years of planning, followed by more than a decade of construction. Magnets had to be engineered to steer protons at near light speed, cryogenic systems designed to cool them to near absolute zero, and detectors the size of buildings created to capture each collision. The final product is the result of patience, persistence, and long-term vision, a reminder that the deepest scientific goals often take more than one generation to achieve. The project cost billions of dollars to build. Constructing the collider came with an immense price tag, billions of dollars shared across the nations of CERN. The figure might seem astronomical, but it represents decades of investment in science and technology. The cost went into materials, superconducting magnets, massive detectors, the tunnel infrastructure, and the thousands of staff who made it possible. And yet, compared to the budgets of military projects or space exploration, the collider's price is modest. Its value lies not only in the discoveries it has made, but also in the spin-off technologies it has produced, advances in computing, materials science, and engineering that ripple outward into medicine and, quote, industry. The price of the LHC is, in many ways, an investment in knowledge itself. Yet its discoveries are priceless windows into reality. For all the billions spent, the true worth of the collider cannot be measured in money. Its discoveries, from the Higgs boson to the nearly perfect fluid of quark-gluon plasma, are priceless glimpses into the fundamental structure of reality. They answer questions that have lingered for decades, and they raise new ones that will shape physics for generations to come. Beyond their scientific importance, these discoveries enrich human culture. They remind us that curiosity is a value in itself, that knowing how the universe works is part of what it means to be human. No price can be set on that kind of knowledge. It is not a commodity, it is a gift to all who wonder. The LHC remains humanity's greatest machine for unlocking the secrets of the universe. In the end, the Large Hadron Collider is more than steel, magnets, and tunnels. It is the culmination of centuries of scientific progress, a tool built by many nations to answer questions older than civilization. What is matter made of? How did the universe begin? What hidden laws still await discovery? The collider does not guarantee answers, but it gives us the means to look deeper than ever before. As of today, no other machine rivals its power or reach. It stands as humanity's boldest step toward understanding the universe at its most fundamental scale. And while future machines may surpass it, the LHC will always be remembered as the moment when human curiosity built a machine vast enough to glimpse the smallest things. And so, our journey through the world's most powerful machine comes to a quiet close. From the moment protons were first set whirling through its vast underground ring, to the instant they collided in flashes hotter than stars, the Large Hadron Collider has carried us closer to the hidden fabric of the universe. We've drifted with it through triumphs, challenges, and discoveries, seeing not only the machinery but the people and the imagination that make it alive. As the night deepens, it is comforting to remember that this machine, though mighty, is ultimately a human creation. Thousands of hands and minds from every corner of the earth came together to build it, each one contributing to a greater whole. In that sense, the collider reflects the best of us, our curiosity, our patience, our drive to understand. It is not only a scientific instrument, but a monument to collaboration. Let those thoughts be gentle company as you rest. Imagine yourself standing at the edge of the collider's ring, deep underground, listening to the soft hum of superconducting magnets. Above you, the stars turn quietly over the Geneva night sky. The machine continues its work, sending particles into motion, unraveling mysteries, while you drift away into your own quiet universe of dreams. If you enjoyed this gentle journey tonight, you might consider liking and subscribing, or leaving a thought in the comments below. It helps others find their way here too, one sleepy soul at a time. But there's no need to think about that now. The day is done, the questions can wait, and the vastness of the universe will still be here tomorrow. So let your breath fall into its natural rhythm. Let the last of the day's noise soften and fade. You are safe, you are at rest, and the cosmos itself feels a little closer now, woven into the calm around you. Thank you for joining me tonight, and for sharing this quiet moment of wonder. May your dreams be gentle, and may your curiosity carry you onward, in waking and in rest. Now, if you're ready, let's drift into sleep.